In this video, we will learn about the phase diagram for differential equations. Okay, so many non-linear differential equations cannot be solved explicitly as a function of time. Phase diagram offers a qualitative information about the stability of the equations that is helpful in determining whether the equation converges to an intertemporal or what we call the steady state equilibrium or not. Okay, let us say we have this non-linear differential equation. Okay, y dot is equal to minus y square plus 6y minus 5. Y dot is simply the time derivative of variable y. Our endeavor is to see how this y dot moves on this graph. Okay, so let's write y on this side and this y dot, that's time derivative of y, on the vertical side. Okay, our endeavor is to see how this y dot moves along this graph. That is, we want to identify the points where y dot intersects this horizontal axis. Okay, so for that, what will we do? We will set y dot is equal to 0. Y dot is equal to 0 implies this minus y square plus 6y minus 5 should be equal to 0, which gives us, if I multiply both sides by minus y, it will become y square minus 6y plus 5 should be equal to 0. And using the quadratic, or let's factorize this out here. I can write it in this fashion, that is y square, sum of the two numbers should be equal to the middle term, so we can write minus 5y minus y plus, in place of 5 I can write minus 5 into minus 1, and it should be equal to 0. So factoring first two terms, so y minus 5, here we take minus 1 common and we are left with y minus 5. We set it equal to 0, that is, we got y minus 1 is equal y minus 1 and y minus 5 is equal to 0. That means y, so in place of either y is equal to 1 or y is equal to 5. Okay, so let's write in place of y, let's write it as y1 is equal to 1 or y2 is equal to 5. Okay, so we got 2 pointers. Okay, so we identified 2 pointers where this y dot intersects the horizontal axis. That is when y1 is equal to 1 or when y2 is equal to 5. Okay, now there are two things here. That is, y dot can intersect the horizontal line in two ways. Okay, so let me write it here. So this y dot can intersect horizontal axis, this horizontal axis, sorry for the spelling mistake, in two ways. Okay, so simple thing. First, if we have this graph, y dot can intersect this horizontal axis. If it is y, it is y dot, so it can intersect on this side in this fashion. Okay, so this point and this, if this is our y dot, or it can intersect in this fashion, that is in this fashion. Okay, so this is our y dot here. So we got 2 pointers for y, 2 pointers where y dot intersects this horizontal line, but it can intersect in two ways. Either it will be a u-shaped curve or it will be inverted u-shaped curve. Now we need to determine whether the point is a minimum point or maximum point. Okay, for that, what we want to do, we want to optimize this y dot. Okay, so we want to find out whether this y dot is at maximum or minimum. For that, what we do, we simply take the derivative of y dot. So let me write it here. First order condition for optimization requires there dy dot upon dy should be equal to 0. So taking derivative of this function, rather dy dot upon dy, so we got minus 2y, that is minus 2y plus 6 should be equal to 0. That gives us 2y is equal to 6, which implies y is equal to 3. So y is equal to 3 is our critical point. Okay. Now, first order condition does not tell us anything about the minimum or maximum. For to find whether we have minimum or maximum, we need to check second order condition. Okay, second order condition is simply we take the second order derivative. So this is our dy dot upon dy. Okay, this is our first order derivative. Now second order derivative will be d square y dot upon dy square, and we want to see what is the sign of this second order derivative. Now if this is first derivative taking second derivative with respect to y, so we will be left with minus 2, which is less than 0. Since second order derivative is less than 1, sorry, less than 0, we can say our y dot you know, our y dot function will be maximum. Okay, so we can say it is at relative maximum. That means we can now draw the graph of this y dot, and it will look like this. Okay, so this is our y dot. Now to check for the stability, for stability condition for this y dot, there are some rules. Okay, so first rule is that if this y dot graph lies above the horizontal axis, it moves towards right. That means the arrows point towards right. Let me repeat it again. If okay, the portion of the graph of y dot which is above the horizontal axis, the arrows of motion will point towards right. That means here from this point it is above the horizontal axis, so we will point the arrows of motion towards right. Here up to this point we have this y dot above the horizontal axis, so here we will also have the right, the arrows of motion will point towards right. First thing. Second is, if y dot graph lies below the horizontal axis, the arrows of motion will point towards left. Okay, here you can see from this point y dot is below the horizontal axis, so the arrows of motion will point towards left. Here from this point the y dot is below the horizontal axis, so it will point towards left. So left is this side, so here it will be left in this case. Okay, what was our critical point? And let us see here, we got also the critical point is 3. At this point we got two values, y1 is equal to 1, here we have y2 is equal to 5. Okay, now we observe the direction of the arrows of the motion. Okay, here at at y1, and let me write it here, this is our y1, this is our y2, this point y2. Okay, at point y1, since the arrows of motion point away each other or they deviate from each other, okay, we can say that y1 is not a stable equilibrium. Okay, if the arrows of motion are moving towards each other, then we have the stable equilibrium. Okay, at this point at y2 the arrows of motion are pointing towards each other. Then this point is stable, and this point, since the arrows of motion you know point away each other or they deviate from each other, it will be unstable at this point. Okay, so let me repeat it again. First, as I told you, non-linear differential equations that cannot be explicitly solved as a function of time, we use the phase diagram. Okay, since this was our non-linear differential equation, so first step was to set y dot equal to 0. When we set it equal to 0, we got two values for y dot where it intersects this horizontal axis, that is when y1 is equal to 1 and y2 is equal to 5. Okay, now we want to make sure whether our graph is inverted u or it is u shaped. Okay, as I have told you, y dot can intersect a horizontal axis in two ways. Either our graph will look like this, which will be a minimum, or it will be like this, which will be a maximum. Okay, we want to make sure whether we have the minimum, uh, yeah, we want to find the minimum point or maximum point. For that, we optimize our y dot. Okay, first order condition for optimization requires we take the derivative of this function with respect to y, set it equal to 0. So we got y is equal to 3 as a critical point. Okay, so first order condition does not tell us anything about the maximum or minimum. For that we need to check the second order condition. If the sign of the second order derivative comes out to be negative, in this case it came out to be negative, then we can say we have a maximum point at critical point. Okay, so our graph will look like this. If it was less than 0, then we would have a minimum point in this fashion. That means we would have this graph if second order derivative came out to be positive. Now we draw the graph here. Okay, our y dot crosses the horizontal axis at 2 points at y1 is equal to 1 and y2 is equal to 5. Now we want to find out the stability condition. Okay, now we apply the rule, that is, as I told you, if y dot graph lies above the horizontal axis, okay, the arrows of motion point towards right. Okay, so the arrows of motion point towards right up to this. And if y dot graph lies below the horizontal axis, the arrows of motion point towards left. Okay, you can see from this it is down the horizontal axis, so arrows of motion will point towards left. Here it will also point towards left. Now if the arrows are deviating from each other, and we can see at this point, then y1 cannot be a stable equilibrium. And if the arrows of motion point towards each other, then this point y2 is equal to 5 will be the stable equilibrium. Okay, so I hope I make myself clear in this video. Thank you.